This is a number theory question from IMO 1970, question 4. We're asked to find the set of all positive integer n's with the property that the set of 6 consecutive positive integers, which can be partitionable into 2 sets, such that the product of the number in one set equals the product of the number in other set. What are all possible integer n's? So after we understand the question, I shall delete the question here to make more space for the solution. I'll let S to be the set of 6 consecutive integers, and the set S is partitioned into 2 sets, S1 and S2. I'll let P1 to be the product of all x in S1, and P2 is a product of all y, such that y in S2. And in this case, P1 equals to P2. If these are all possible, then from here, we will get P1 squared equals to P1 P2. P1 is a product of all number in S1, and P2 is the product of all number in S2. So this will mean that this is actually the product of all the number in S. However, in 1937, Paul Ehrlich proved that the product of consecutive positive integer can never be a square. With that result, this is not possible. But we are not going to use that. If you're interested, you can look at the description and get the article from there. Okay, so go back to this. Note that 7 does not divide any numbers in S. Suppose not, there's only one multiple of 7, and it must be either go to P1 or P2. And in one hand, there is a multiple of 7, but the other one does not have a multiple of 7. And therefore, it uses a contradiction. So none of them is a multiple of 7. Then it must congruent to 1, 2, 3, 4, 5, and 6 modulo 7. So it means that P1 squared will be congruent to 1, 2, 3, 4, 5, and 6 modulo 7. We'll see that this number will be congruent to 1 is 1, and 6 will be a negative 1. We combine 2 and 4, and this is equals to 8. 3 and 5, it is equals to 15. And 8 is congruent to 1 modulo 7. 15 is also congruent to 1 modulo 7. And 6 is congruent to negative 1 modulo 7. And therefore, this is congruent to 1 modulo 7. In fact, there's a general theorem called Wilson theorem, say that if this is mod P, and this is the product of 1 to up to P minus 1, then it's always congruent to negative 1 mod P. So P1 is just an integer. The square of this integer is congruent to 1 mod 7. Is it possible? Now we can check one by one. Okay, we know that 1 square is congruent to 1 mod 7. 2 square is congruent to 4 mod 7. 3 square is congruent to 9, that is congruent to 2 mod 7. And we see that 4 square is congruent to negative 3 square, that is congruent to 2 again. 5 square is congruent to negative 2 square, that is congruent to 4. And 6 square is congruent to negative 1, that is congruent to 1 again. So none of this, all this is mod 7. We check the square of any integer. It is not possible to have negative 1 mod 7. It means that this is not possible. And therefore, there's no such n. We try to reduce this a little bit more and see whether it is possible. If we have 4 consecutive integers, it's well known that the product of any 4 consecutive integers is a square number minus 1. So if you have n plus 1, n plus 2, n plus 3, then this will be written as n plus 3, n plus 1, n plus 2. So this will be n squared plus 3n. This is n squared plus 3n plus 2. Let this to be u. It will be u plus 2. So this will be u plus 1 squared minus 1. The product of 4 consecutive integers is a square number minus 1. So this is not possible. If you have 5 of them, then you can use the similar argument like what we have here. If you have 5 elements, then there must be exactly one of them is a multiple of 5. Then on one hand, say P1 is a multiple of 5, but P2 is not multiple of 5, and they cannot be the same. However, if we change the condition a little bit, almost consecutive positive integer, it may be possible. Example, 1, 2, 3, 4 equals to 4, 6. So instead of 1, 2, 3, 4, 5, 6, we have 1, 2, 3, 4, 4, 6. That is possible. Another example, 2, 3, 4, 5, 6 equals to 8, 9, and 10. So this is the end of today's lesson. I'll see you again. Bye-bye.